All right, folks, we are going to continue the conference with our first panel, which is the industry panel, led by Paula Cipierre, and this is about novel quantum applications and use cases.
Well, thank you so much, Maurits, for the kind introduction, and thank you to Stanford Law School for hosting this really amazing interdisciplinary diverse conference on one of the most important technological, I think, challenges and innovations of our time. My name is Paula Cipierre. I'm the Director of Data Ethics and Innovation at Ada Learning, which is a female-founded German startup that focuses on driving the responsible adoption of new technologies through upskilling employees, very much needed in Germany, as some of you might know. And I was actually laughing as I saw Urs's and Constance's presentation earlier about the kind of like digital challenges in Thailand, because I think you could have easily replaced Thailand with Germany and had very similar challenges there as well. My role at Ada is actually to develop executive education programs for government and industry at the intersection of AI strategy and regulation. And one thing that Ryan mentioned in his presentation, of course, as well, is that AI is very much present in the public sphere already, right? So it's something that politicians can sort of connect to as well because they see it in their constituencies as well. I think one of the challenges with quantum, of course, is that it's still very much like in the background, which does not mean that it's not advancing rapidly and that it's not a conversation we need to have with society as well. So it's great that this conference is driving some of that as well. Prior to my role at Ada, I actually led the European Privacy and Civil Liberties Engineering work of Palantir Technologies. And there as well, I witnessed firsthand the importance of bringing together engineers, lawyers, and ethicists to sort of like guide the responsible innovation process in the stage of technological development already. And it's a special treat for me to actually be back in Palo Alto because this is where I started my role at Palantir 8 years ago. So a little trip down memory lane for me. But today we are not looking back, we are looking ahead, and I'm probably not the only one who is particularly excited about this particular panel, because here we will be really learning from some of the most leading experts in industry as to where the current developments in quantum are currently at and how we can sort of ensure their responsible development and use. We don't have a lot of time, so without further ado, I will hand it over to my co-panelists who will share with us some brief introductory remarks and of course introduce themselves as well to tell us all about where we are currently at. So starting with Charina to my left.
Hi everyone, I'm Charina Chou. I am the Chief Operating Officer at Google Quantum AI. I'm very happy to be on this panel. I think it's important, right? We're all here for the day to talk about quantum technology, and really the question that underpins that is like, why? Like, why pursue any of this technology at all? Right, from point of view of trying to build a quantum computer, right? Ryan and others were talking about how much effort and investment is going into pushing the hardware, trying to develop, all the algorithms. Why? It's why pursue building a quantum computer? To quote the Nobel Prize winner Richard Feynman, he says, "Nature isn't classical, right? Nature is quantum mechanical. If you want to build a simulation of nature, if you want to do a simulation of nature, you must make it quantum mechanical." And look, there's this idea of, even with today's best AI, right? And again, we see AI everywhere. Even with today's best AI, it is difficult, even impossible, to simulate a lot of things in nature exactly, right? And I think even, personal example for me, Paula said it was special to be here at Stanford. I was here for undergrad at Stanford also. 20 years ago, my husband, then friend, was facing a very difficult cancer diagnosis. He went through multiple rounds of chemo and radiation here at Stanford Hospital. Actually, nothing was working. Thankfully, finally, he actually was able to go through an experimental treatment at Stanford. It cured him. Fast forward to today, he is an oncologist. He's a cancer researcher. He's working to help other patients, right? And we know not everybody is so lucky, right? There are multiple untreatable cancers. There's lots of other diseases, conditions. And if we as a society had the ability to better simulate nature, if we were able to really, have this capability, we might increase our ability to solve these types of problems, help more people, right? And this is for us, where quantum computers come in, right? The thesis is that quantum computers will be a powerful tool there are a couple of different applications we could talk about. Right? So the first is quantum simulation. I just mentioned this, right? The ability to simulate molecules, materials. And this is demonstrated that it's going to have an exponential speed up. So what that means is, for quantum computers over classical computers, the computation will be performed exponentially faster if you had a quantum computer powerful enough, right? Lots of applications for this, things like drug discovery, but of course also battery design, fusion energy, better catalysts, a lot of different applications here. A second application is one called quantum machine learning. So many people may be familiar with today's classical machine learning. The idea with quantum machine learning is the use of quantum computers to learn from quantum data. So quantum data being things like magnetic data, electronic data, data coming from quantum sensors, right? A lot of this work is happening now too. It's really nice to see all the progress happening in the sensing field. And this application, quantum machine learning, is also expected to have an exponential speed up. Right? So another way to think about that is that quantum computers will be able to learn from exponentially less data, less quantum data than classical computers. That could have enormous implications. Right? Whether or not this is going to be true for classical data, learning from things like text, images, video, things that we kind of know and love today with classical machine learning, that remains to be seen. There's a lot of important efforts going on right now, but has not been proven yet, right? And there's other applications too, right? Other speed ups, and this is exactly what drives us. So I think for Google, and certainly I'm sure many others in the field, right? This is the hope. Our mission at Google Quantum AI is to build best-in-class quantum computers for otherwise impossible problems. And I didn't bring slides today, but I brought some show and tell. So I'll pass these around also. I have some photos of some of our chips that we are using. I actually also brought the device, one of the devices, so we can pass this around just so people can take a look. I think sometimes it's very helpful to see. This is a photo of the package. So the device goes inside of the package and then gets wired up. And then, again, Ryan mentioned the need for cryogenics. At Google, we're pursuing superconducting qubits. So we do aluminum on silicon. These do need to be down to 10 millikelvin. So we have giant fridges to get them down to that temperature. So pass that around as well. Maybe I'll make one last comment and then pass it on to Kevin. To date, right, no quantum computer, none of, even the best processors that exist right now, no quantum computer has outperformed a supercomputer, classical supercomputer, on any real-world application, right? This is an important distinction. There's a lot of efforts going on right now on today's processors, which are great, really important research and learning activities and even, quantum simulation. But to date, none of that has outperformed what you could do really with brute force on a laptop or maybe an hour or so on a classical supercomputer. And there has been one example of a beyond classical algorithm that's called random circuit sampling, but there's no, to date, no real world application known for that algorithm. So that's the hope. That's why we're all working on this. We do think with better algorithms, with better hardware, we can push for more beyond classical applications. Kevin.
Perfect. Thank you so much.
Thanks.
Would you like me to hand this to the audience?
Sure.
Then
Yes.
Can somebody volunteer to pick this up? Then we can sort of hand that around. So over to Sam, actually, is next in line.
Okay. Hi, everyone. It's great to be here. Thank you to the organizers, and thank you all for attending. My name is Sam Stanwyck. I'm responsible for our quantum computing products at NVIDIA. And so NVIDIA, unlike Google and many other companies involved in quantum, we're not building our own quantum computer. What we're doing is building tools to advance quantum computing research, shorten the timeline, hopefully, to useful quantum computing, and hopefully broaden the space of useful quantum computing applications, and attempting to work with everyone who is building a quantum computer and everyone who's doing that research and developing applications to accelerate their work. And what NVIDIA has also done for a couple decades is do this sort of thing broadly in other accelerated computing domains. And I thought some of that was relevant to how we think about this early stage of quantum computing. And so NVIDIA invented the GPU. The initial application of that was graphics and video games. But around 25 years ago, some smart researchers started realizing that you could use GPUs to massively accelerate some things that they were doing in scientific computing. And so this was exciting. It was also extremely challenging. You had to be a real expert to figure out how to do this. You had to hack these things called programmable shaders, wire up an Xbox for something completely different. It was unnecessarily painful. So what NVIDIA did is invented a programming model called CUDA. And in a nutshell, what that did is it said, okay, if you can program in C, or eventually C++ or Python or anything else, now you can use a GPU. And so massively broadened the space of people who could use GPUs, made them much easier to use quickly, and turned GPUs from kind of a niche research tool into something that's at the heart of almost every supercomputer and a lot of scientific research today. There was a similar sort of path in AI, where maybe 15 years ago, some researchers realized that GPUs could provide a massive advantage for training, at the time, convolutional neural networks. And so NVIDIA saw this and said, how can we invest to help this community? And actually, one of the first systems that we built called DGX was hand-delivered to a very small startup at the time called OpenAI. And the availability of GPUs, the broad availability of GPUs meant that a much larger group of people could train these models and move deep learning forward. And obviously, we've seen what that's resulted in. And what these have in common, and what they have in common with quantum computing today, is we try to invest in these emerging technologies long before they're very valuable. So I think Charina kind of excellently expressed where we are in quantum computing in terms of useful applications and the timeline to get there. I agree with that. And our goal is to build the tools to accelerate that, create the access to systems and resources that every researcher and every quantum computing group needs to help us get there.
Perfect. Thanks so much for that introductory overview. Over to Florian.
Thank you very much. So thank you also for having me. It's great to be here. I was here last year. It was great last year as well. So I'm very happy to see how this evolves. I brought a few slides that I will walk us through today. But first things first, my name is Florian Neukart. I'm Terra Quantum's Chief Product Officer. Terra Quantum is a quantum technology company. We're active in all pillars of quantum technology, depending on how you define it, but that is quantum computing, sensing, imaging, and cryptography, and in hard and software development. And besides, I work at the University of Leiden, where I've been a professor for quantum computing for 10 years now. So just as a summary, what we do is we provide quantum technology as a service whenever that is possible. It's not always possible, depending on how you look at things, but quantum computing, for example, is one of these technologies where you can supply everything from the hardware to the software until the integration into existing environments. We split that, our service offering, in algorithms. So we strongly focus on hybrid algorithms. So it's not pure quantum algorithms. When you think about all the classical computers that are out there in the market, all these things that they can do well today, they will also do well in the future. So it's always a combination of quantum and classical computing, very much like it's a combination between CPUs and GPUs. So add QPUs, quantum processing units, to that stack, and you have another kind of special purpose computing device. It's an evolution of high performance computing. We offer computing solutions, so we offer the hardware, the hybrid cloud. We operate data centers. For us, quantum computing is a data center technology. You'll access it through the cloud as of now, also depending on hardware constraints and how to operate this system, or the requirements that they have to operations. We see that as a cloud technology. And then our security offering, lastly, so that comprises all quantum key distribution and classical algorithms to prevent attacks from quantum computers once they're strong enough. The areas that everyone is looking into, that's not specific to Terra Quantum, of course, and we heard about that today already, are these three, is optimization, machine learning, and simulation. And simulation is the topic of today, but I just briefly mentioned optimization. That's where many people started, utilizing practical quantum systems to hybridize, because that's where the most power was immediately available. Many of the problems that we see in the world can be translated into an optimization problem, and that makes it very beautifully expressible also for quantum computing systems. In machine learning, we think about these large language models, of course, when we talk about today's AI applications, but there are others, as we just heard from Stan, like convolutional networks, image classification, smaller models, still very complex. So we can hybridize these efficiently today and outperform purely classical models. So very important, it's not everything expressed as a quantum circuit, as something that can be executed on a quantum computer, but we use simulated quantum processors or physical quantum processors, depending on the use case, to create these hybrid algorithms. And simulation. So simulation that goes beyond, or at least for us, goes beyond pure quantum algorithms and hybrid quantum algorithms. We also look at quantum-inspired algorithms. That's a different class, where you still have classical processing, but you take processes that you observe in quantum physics that you try to mimic classically to achieve performance advantages. One of these classes of algorithms that is very prominently used in all areas of quantum computing is tensor networks. Tensor networks originally come from physics, where they were expressed to model many-body physical systems, but now they found their way into all the algorithms that we look at. And what you can do with it is very beautiful. So if you think about a problem, say you look at molecules and their behavior, then you can express that problem as a tensor network. And that still means we process it classically, it's quantum inspired, but now it's also been found that these tensor networks can be effectively translated into quantum circuits, into something that can run on quantum computers. Also with the classical tensor networks, we outperform. So for example, when we look at torsion angles or bonds in molecules, we outperform classical benchmarks such as CREST. But then when we translate these into quantum circuits, once the quantum chips are powerful enough to process these, we will have significantly more advantages. One example that I brought here is find the optimal 3D structure of a molecule. So when you think of a molecule being composed of many atoms, then there are many things that you can do with that molecule depending on the angles, how you orient the planes of that molecule, so torsion angles, bond length. So these are things that we look at. What's the optimal configuration? And that is something that we can do with tensor networks, and in consequence, something that we will then at some point, once quantum computers are strong and powerful enough, process on quantum systems. So what I want to say and what I want to give as a giveaway today is that already today, using hybrid quantum computing, combination of classical and quantum computing, plus an operating system on top that handles load distribution, plus the algorithms on top, we can already outperform classical systems. One last thing, just as an overview, and if we want to talk more about that, we can in the break. This is not exactly quantum simulation, but it's another simulation problem that we looked at. It's chemical mixing. And the problem is as follows. So when you do chemical mixing, bring compounds together, there are many parameters. There is the pressure, there's the temperature, there is the sequence of how you mix it, there are these angles of these chemical mixers. So what you see in that picture here is actually a physical device, a chemical mixer. And what people usually do is design that using a simulation, then experiment, see what goes wrong, take that data, bring it back and redesign and do that again and again. And using a hybrid algorithm, we could reduce that by 45%, which means you save material and costs, of course, in terms of the people that develop these simulations. I'll skip over these last ones, but suffice to say, there's many more things that we can do with hybrid quantum computing already today. Thank you.
Thank you, Florian. I already saw like the last couple of slides, a couple of use cases I think we could probably delve into as well in the breaks and throughout the day as well. But last and certainly not least, Kevin, why don't you share with us some perspective from Daiki as well?
Sure. Thank you. Let's see if the slide's up. Yeah, let's just start out why we're here. as the founder, well, one of the funders and funding of the actual institute and the sponsor of the event. The reason why we're here, our genesis story in a sense, is we come originally from Austria, Vienna, machine learning and data science company, but we found kind of going it alone was quite tricky. So we think multidisciplinary approach is a bit broader speaking, is a more important role, quantum as long as machine learning. So we founded Daiki about a year ago. It was a successful research spin-out project from the University of Vienna. I'll go into Mark Kuckelberg. He's the head of ethics at the University of Vienna. I've read many of his books. He's quite interesting about AI and ethics and how that role plays. So we started work with ethicists, then we reached out with Moritz as well, bring in Stanford Law to bring in the legal aspects, and we focus mostly on the machine learning, the AI side of the business. What we developed is a platform that enables people to, let's say, take a recipe approach or a holistic approach at these possible scenarios. So we really start with getting AI done. We're scientists, but based on in a practical sense with clients and have a successful business in that sense. So we're looking how can we bring these responsible elements into those factors, with quantum being obviously a future goal. That's some of our team. I mentioned Mark. Moritz is here. These are the founding team members, partly, myself included, kind of based around that. What it does is it focuses on existing compliance and risk issues as well. So we have ISO standards, other things that are coming out that are new. How do we bring those to a company? Because a lot of challenges we have from management and people and staff is they're either focused on tech or focused on legal, but there's no overbridging, arcing elements that are at place at times. So we're trying to bridge that gap with some structured, let's call it the EQMS methods. This, hopefully will start here. It's just a little demo of what the platform looks like. And what we've taken here is we've taken the work they did on the 10 steps and just built it into the platform. We have a knowledge base that we can use. We can bring in academic research and papers into this knowledge base. We've developed a proprietary RAG system that allows people to just query those different documents. So it has a chatbot system you'll see here. Takes them step by step, the different kind of recipes that are in play, helps people document, collaborate with team members, and actually start to work on these processes. Obviously, can query people, because we have a big gap in the industry between people in the know and people not in the know. And as we bring more people into this environment, we need to educate them and take them by the hand partly of the way. So this is just a quick demo of things that could help anyone in an organization asking questions to go about their business or understand, in this case, more quantum more clearly. You can see the RAG works quite well so far. Based on a lot of privacy issues, we have IP issues as well. So this is why we kind of did a standalone system here. Great, so you can see some of the questions just coming through. Basically, what is quantum technologies? Varying degrees of success here for people within the industry to understand these kind of things. And what it does, it really brings is a uniform system for people to collaborate and work on these projects, multidisciplinary. Great. This is we have a toy, I would call it, for the team. It's a hybrid quantum computer from QMware. It kind of just gives a simulation effect of what quantum is in that sense. It's kind of the team really enjoys playing with it, and we have some customers. We have use cases in healthcare. We have people that are excited in manufacturing and actually interested in construction. So there's a few people that we would be surprised ourselves that are kind of looking at the quantum cases, thinking 5, 10, 15 years out ahead, how it impacts their business. You mentioned the healthcare issue. That's really fascinating. A lot of universities we talk to, there's a massive disconnect between people doing cutting-edge research, whether it be diabetes or cancer or whatnot, and applying even modern technologies. We have people that are working still with Excel, not even using AI. We're sponsoring some kind of hackathons in AI sciences just to promote these environments because there is a gap. It's shocking to us as well, and we're trying to promote that as well. So that's where we hope to help. Yeah, that was all from my side. I'm hoping you have questions. Thank you.
Thank you. No, thanks to you all for giving us sort of like a broad overview as to where we are currently at in the industry. Of course, the title of this conference is Responsible Quantum Technologies, and we heard this morning as well from Urs and Elina as well about sort of different frameworks for advancing quantum technologies responsibly, but also a lot of uncertainty still around what the kind of risks are that we might be confronting in the near to medium term. So I would be really interested to hear from you as well. What do you currently think are the biggest risks in the quantum industry? And what are you doing perhaps in your respective areas or fields to meet those risks, either by safeguarding specific values, engaging with societal stakeholders, also government, and engaging maybe with academia as well. So maybe we'll actually do it in the reverse order. So Kevin, you're on again. I know you already touched upon a couple of these topics, but maybe you can go into further detail.
Yeah, I think, as you mentioned, the various factors. I mean, it starts with government, starts with regulation. and then starts with the industry. But industry is only moved when I think it starts to affect the business value. We see people that are, we had a long time where the executives were working, knew that the machine learning, the data scientists, AI, quantum, if they exist, quantum team existed, but there's a big disconnect what they're actually up to, what this team is doing. So kind of opening that transparency and explainability of it has been crucial from our side, and then getting them into the actual room to talk about it. And now we have the EU Act in Europe, we have ISO 42001 coming. These are kind of standards that are coming out that people are starting to be aware of. And we are hoping that people aren't kind of retroactively trying to things, less of an audit mentality and actually preparing for these tasks. So that's why I think this holistic approach is important to bring people from to various departments, including legal, including if there's an ethicist, HR. In Europe, we have Workers' Council. They're involved in every conversation now. That's a new one for a lot of people, that the Workers' Council is actually involved. How can we use AI at this case, but eventually it'll be a quantum, and how do we invest in these situations?
Yeah, thank you. And obviously the AI Act is an interesting example as well, because that's a very sweeping piece of regulation that has not necessarily been viewed uncritically as well, just because it's sort of like interfering at a stage of technology development, which might also hamper the European innovation ecosystem.
We're pro-regulation on our
Yeah.
side. We find it offers clarity, so we support all the regulations, and in the software itself, we kind of allow people to follow those regulations clearly, because that's something been missing, particularly on the tech side.
Yeah, but I think it's a great example as well, where it's important to engage with regulators as well, such that regulation is structured in a way that is also sensible from an industry perspective and enables innovation too. Florian, what is your perspective on the sort of responsibility side of quantum development?
Yeah, so I completely agree. I think engaging with regulators is very, very important. So also when we look at existing applications in the fields of machine learning specifically, quantum computing, like many other of the computing technologies that we saw over the last years enter the market, is an enabling technology. So it's not quantum computing versus AI, it's quantum computing enabling AI. And that is true for many other applications as well. And the question that we have to ask is, of course, so what are the good things that we can do? But then, as any technology, as we heard today already, it can also be used for the bad things. And one of the bad things that I'm specifically worried about is exploitation of data. So we heard too that quantum computers will allow to learn, so at least when it comes to quantum data, will allow to learn from algorithms to learn from less data. We observed that in classical data already. So when we think about this example that we had before of hybrid convolutional neural networks, for example, where we learn from images to classify images. So here what we see in hybrid algorithms is that we can learn with a lot less data because we have a higher expressibility in that one part that is processed quantumly in that network. So imagine as a network has many layers, you take one layer, express that as a quantum circuit, and compare that to the purely classical one. Then with that new one, the hybrid one, you can learn from less data and be more accurate. So that brings some risks. And the second one, it brings advantages too. The second one that is very important in my view is security. Because you've heard all of us discuss that all the time, that quantum computers, once powerful enough, pose a threat to current encryption method. To what extent that also remains true for the currently by NIST proposed and evaluated post-quantum cryptography algorithms remains to be seen, but we can, as of now, not be sure that all post-quantum cryptography algorithms, so those where we think they're mathematically strong enough to withstand an attack by quantum computer, are really quantum secure forever. So how do we integrate quantum technology in this loop? So how can we, for example, use quantum random number generators in such algorithms? How can we use long-distance quantum key distribution to securely exchange keys? Because here, at least, as long as the laws of quantum physics don't change, we are very certain that we can prevent attacks, see attacks. So these are the things that I'm very much worried about, but also very hopeful.
Thank you. Sam, what's the viewpoint of NVIDIA on these points?
Sure. I'll warn you before I start that I'm a physicist who usually thinks about enabling this technology rather than regulating it, and I don't have anything to add to Kevin and Florian's excellent perspective. So maybe I'll say something a little bit different. I think with quantum technology, it's early stage enough that there are a couple of known risks and then a bunch of unknown unknowns, and so those should be handled differently. I think maybe the most concrete known risk is security. So a quantum computer, which is cryptographically relevant, and NVIDIA is very involved in helping to tackle that. And what most people are doing is looking at ways to replace our current asymmetric cryptography, which is vulnerable to quantum computers, with new asymmetric cryptography algorithms which aren't. So this is called post-quantum cryptography. We actually just released a new library that accelerates all of the leading post-quantum cryptography algorithms on GPUs. And what this extra performance enables you to do is to trade performance for security. So these new algorithms are promising but less proven. If you can run them very performantly, you can run many at once, you can run different types, you can switch between different ones easily. And so if we're worried about kind of hack now, decrypt later attacks where someone might take your data now and wait for a cryptographically relevant quantum computer to decrypt it, this technology can be adopted today without losing anything. The second concrete risk that I see is a bit of a zag, maybe, which is misallocating the massive resources that are going into quantum computing. So it's wonderful that government, industry, everyone is starting to invest heavily in quantum computing. I think that there's quantum computing is maybe unbiased, but maybe uniquely hard to understand for someone who's brand new to it and challenging to explain briefly. And so I think there's opportunity to as some speakers have talked about earlier today, kind of chase very near-term things that seem promising versus kind of the big long-term highest value, I would say, effects of quantum computing, which are around likely simulation of materials for the purposes of drug discovery, energy efficiency, and the like. And so I don't have a solution to offer, but that's something that we're thinking about as we prioritize our work.
Thank you, Sam. No, that was really helpful. And then finally, Karina, where does Google stand on this? I imagine very much at the forefront as well.
Yeah, I'd just say I agree with a lot of the previous comments, maybe add a few more thoughts. The first is in terms of risks. Elena had a nice point earlier on kind of the, responsible innovation means like responsibility to innovate. And I think that is this idea, right? What a risk is that we don't invest, the right way, as Sam just said. We don't innovate with the resources at hand. I think we recognize quantum computing or quantum technologies broadly it's an enormous problem, right? No one company, no one organization can do this on their own, and no one country can do this on their own. Maybe I'll add one specific, piece of color to this. We at Google, we're pursuing, as I said, superconducting qubits, and to cool these down, you need to get these massive cryostats. At Google, we are excited. We're very excited about our quantum processor technology. We think this is, where we've got a lot of expertise, but we don't have expertise in the cryogenic systems. We don't necessarily have expertise in all the wiring and other applications. We've actually been partnering with others in Europe and in Asia to develop these things, right? And so I think, one risk really is that we don't innovate the right way, we aren't able to partner the right way, and it's important for companies to work together with academia and also governments to get the right rules in place so that we, as society can really push the technology. Second comment, I think Florian and Sam both mentioned encryption. Obviously, this is on a lot of people's minds, so maybe I'll just add, our at least best estimates today seem to suggest that you need on the order of 10 million physical qubits probably, and 10 to the minus 6 logical error rate. That is one error in every million or more algorithmic steps. So our guess is this is 10 or more years away. However, it's not too soon to act now, right? There's a lot of work that needs to go into it. I just kind of comment, we really appreciate the efforts from NIST and a lot of people who've been collaborating with NIST, that agency really leading the effort to try to figure out post-quantum cryptography. And then maybe the last point I'd make on the risk, also going back to something Alina said earlier, is maybe a risk is not everyone has a chance to engage, right? Everybody does not need to understand quantum computing. Not everybody doesn't need to know how to build a computer, but our hope is that there are applications that do implicate have an opportunity for everyone. And so really starting now to make sure we're having those conversations, bringing in people from all different perspectives to really think about engagement seems critical.
Yeah, no, I really appreciate the point about inclusivity and also bringing in a diversity of perspectives. I'll ask one more question sort of like to the panel, and then hopefully we'll also have some questions from the audience as well. It's a great opportunity with this fantastic panel here. But maybe if there is one wish, or like a kind of like wish list you could give to the government side of this, government actors, like what is one wish you would like pass along to government actors at this stage? And I won't sort of like give an order here if any one of you would like to answer this point. Your chance to.
I guess we'll go in the same order maybe. Balance, I think,
Yeah.
is the key word from my side, is that their involvement, but at a respectable distance and whatnot. I think policy and governance is key. Funding is obviously crucial, particularly to smaller markets, smaller industries. That means alignment with universities and such, but a healthy respect for it as well. Knowing when there is a gap in knowledge or understanding. I think we heard from our policy person earlier today about the challenges in most countries with that. So I think, yeah, being open to these new technologies is the key, and the balancing of understanding when to approach it and when not to. Yeah, that would be my high-level answer.
I can go. So I'll add consistency. I think is needed. I think quantum technology is right now a natural fit for government investment. It's something that has massive long-term benefits that might be hard to quantify nearer term. But in order to make progress, I think, or make progress all the way to useful quantum computing, it can't be invest for a little while and then we haven't got to useful quantum computing in 2 years, and so we stop and move on to the next big thing. I think that doesn't work for startups who are driving a lot of the innovation. That doesn't work for academic research groups who are driving a lot of the innovation. I think, I certainly agree. Balance is key, but also understanding that this is going to take some time and there won't be immediate returns, but the long-term payoff is worth it. And so, consistency of investment.
Thank you. I would say, so these two words, coordination and cooperation. So cooperation with industry, I think, is very important, and many governments do that really well. So here in the US, I feel it works very well. But then our companies, and that's where I can speak about too, we are very active in Germany. We are a German company, German-Swiss company. So here sometimes it seems not very coordinated. And that may differ, again, from government to government. So what I really think is important for governments is to have an open ear, also when it comes to specifically security, so cryptography, because in the end, if we think about the application of this technology or deployment of secure technologies, it is not only about corporate networks, it is not only about small pieces, it's the whole communication infrastructure globally that has to be adopted, that has to be changed, and we have to start doing that now. And sometimes the feeling is, and that's not only the experience I have with governmental institutions, it's also with industry, sometimes the feeling is everyone is waiting for something to happen, something big to happen, the one big incident, and only then we can become active. Because then we know the technology is there, but that's too late. So I feel it needs to happen earlier, and that involves dialogue with industry, with the people building that technology and bringing it to the market. I think that would be, from my view, most important.
Yeah, it'll be interesting to see what the ChatGPT moment of quantum will be, that is sort of like get regulators going.
Maybe, yeah, I'll add international collaboration. So look, I think, a number of us, we talked about national security, and certainly from the EU, we hear things like digital sovereignty, and, those are all important acknowledgements. I think it's also, just want to emphasize this point, right? No country is going to do this on their own. We've got to cooperate and got to, work with governments to really be smart about what are the ways that we can exchange talent, exchange ideas, exchange parts, so that, we as a society can really have these tools. You think about some of the applications that we've been talking about, right? Even just quantum simulation, which again is the theme of this conference, you really want to make a dent in, things like drug discovery or climate change. Like, that's everybody's problem. So how can we all work together? How can governments really figure out the right modes of international collaboration to bring about the technology?
Thank you. Yeah, so we have balance, consistency, coordination, and cooperation, and international collaboration. It sounds like the new elements of maybe a new framework that can be further explored in academia as well. We have about 10 minutes left, so maybe there are some questions from the audience. Oh, perfect. Go ahead. Is there a microphone as well? Yes.
Speaking for us from the young generation, if you from industry recruit people for quantum, what skills would you like us to have, or generally to be educated in universities?
Great question.
If I may start. So what we're looking for is not that everybody has to be a quantum physicist. So the state of the technology, as we heard today, is very often or compared to analog computing a long time ago, or maybe even assembly. So let's put it that way, assembly and programming assembly. But this will evolve, so we will have more advanced tools. So I would always say a technical background for those who work technically is very, very helpful, an engineering background, but to say everyone has to be a quantum physicist, I don't think this is needed anymore. Also, it's non-technical roles, because we have to bring this technology to the market, we have to be able to explain what it does, and sometimes I come from a technical field, I'm a physicist as well, we're not very good at explaining why would you want to do that. So I think that is very, very important. And also those folks who can think in use cases. So I think that's most important. And this is my experience that I made with Terra Quantum. We always went into these customer calls, talked about, oh, we have this great quantum technology here and there. We have 150, 200 quantum physicists, and I lost half of the audience within the first 5 minutes. So when you talk about use cases, I think that matters. That is what a company wants to understand. What can I do with it? How much money can I save? What's the cost of operation? So all these things. But when you build the technology, you don't necessarily think about it from a technical point of view. So I would also say everyone who can communicate that well and understands well, what is it really that I can do? And how can I get the interest of someone? That matters to me, or to us.
Essentially translators.
Yeah, I was just going to add, if you or any others in the audience are interested, I will say at Google we're hiring right now, so please check out our website. I agree with everything Florian said. I just know also, we're actually interesting is Google also started very researchy, with a group of research scientists, and now as we try to scale up, we're increasingly hiring more engineers, more technicians to work in our fab and on our hardware, and then also, developers, this idea that Florian raised of, how do you actually use the technology? So yeah, happy to chat more at the coffee break too.
I think we have one more question over there. So,
I do as well.
Oh, sorry, yeah.
Yeah, that's good. Shall I go? I'll stand. Thank you, Suzanne Lloyd-Jones from the University of New South Wales, Sydney, Australia. Thank you for a very interesting panel discussion. It was great to hear you all. My question goes to the coordination and cooperation, the consistency and balance points that each of you made. So what is the framework for cooperation between industry and government, that you envisage or that you have in your minds, and what would it look like? And how do you see decisions being made, sort of now and thinking ahead? Thank you.
Perfect. And then maybe we can just take the gentleman's question as well, and then we'll do a final round of answers.
Yeah. We have a panel later on national security and governance issues. So we will also, I think, see competition between the governance of this technology in the world, because we need a healthy ecosystem to drive this, right? It's again about this over-regulation, under-regulation. And of course, we also have to ask a question, in which phase are we? Is it more like as open as possible and as closed as necessary, or as closed as possible and as open as necessary? Where do you think we are, and how should we reach the right balance here?
Oh, okay. Great questions. Well, final round, maybe we'll just go down the line, starting with you, Karina.
Sure, yeah, both good questions. I just maybe emphasize the, working with it between industry and government obviously is critical, right? And your question on, what is the framework for doing that? I think as direct dialogue as possible for us, it seems very, very important, making sure that all the conversations are happening. You asked, how is it going so far? I think, every country is kind of obviously in a different state, but we have been pleased, for example, to see a lot of interaction even between the US and Australia, both on the government and the industry side. Those types of bilateral and multilateral conversations seem very important. So more of that. And then to the question over here, yeah, I think it's a very good point. I think right now probably where it is landing is more like close as possible, open as necessary, and I think very understandable. So just the more that we can have the direct dialogue within those confines seems important.
Thank you. Kevin.
I think we have some issues. Obviously, data privacy is a major driver for all this. Tech sovereignty is a questionable thing, pushing open source, for example. How do we work on these collaboratively? I think by definition they are. That is a framework. As mentioned before, bringing in other aspects, legal, ethicists, social sciences, has been failing, I think, to this point, but I think that's an open opportunity that we can work with. But it means that we have to take kind of the government role. And there's some of the government will be leading on some things, but a lot of times the industry will be leading, we find them, or much farther ahead, so that we have to bring the two together, I think so. And there's others that are just simply waiting for government to say, which is limiting innovation, which is a problem. But by communicating, I think we can work on that.
Great.
So in terms of coordination, so one thing that I observe is, I mean, we all know quantum technologies in general is very popular right now. Because it's so important. It will change so many things, affect so many areas, but that also means there are many stakeholders popping up and being interested in it. And what I see is that not always in every government there is one central hub, so to say, to organize all that funding, to organize all that activities. I see a lot of double work, which means also tax money goes into that double work. Same initiatives pursued by different institutions, and many times, of course, pursuing the prestige of the own institution, so getting publications out, etc. So in terms of the coordination, I would wish for a better collaboration here, better organization here. And in terms of the second question, how open or closed we should be, especially when it comes to security and cryptography, my feeling, and that's not necessarily everyone's feeling in my company, would be as open as possible, because the cryptography world has always been a world that is very open. Every algorithm can be understood. Everyone has to understand how it works, otherwise they won't deploy. So, and that is true, in my view, for quantum technology as well. Only because anyone can understand doesn't mean anyone can hack. That is not true. So the more understand, the better, I feel.
Perfect. And then, Sam, you have the final words.
Perfect. So both excellent questions. So to the first one, I'll agree and maybe build off what Florian said. I think where government can be a big help is enabling international collaborations. A speaker earlier said something along the lines of there just aren't enough quantum experts in the world for each country to try to do this by themselves, and it's hard enough without each country needing to reinvent the wheel, and there are particular countries that have expertise that everyone should benefit from. So, for example, the company that makes the cryogenic systems that most of the superconducting qubits and groups in the world use is based in Sweden, and so enabling kind of easier collaboration between companies from different countries and worldwide, I think, is critical. And to the second question, I agree with Charina that so far it's been closed as possible, as open as necessary. But I do think it's moving in the direction of as open as possible and closed when necessary. I think in order to properly incentivize innovation, some things do need to be closed, and that's okay. But as this becomes a mature technology, and to enable kind of the things we talked about in the first question, as far as collaboration, I think everyone's realizing that opening whatever is possible is beneficial to everyone, and so I'm hopeful about the direction in that case.
Thank you. I love that we're ending on a hopeful remark, and I think the conference is really leading the way here. So thank you very much to the entire panel. I thought this was a great round of insights, and thanks to the great questions from the audience as well.
Thank you so much, Paula, for moderating this fascinating panel, and thank you, Charina, for bringing the Sycamore chip. Thank you. We have a short break with interlude by Karolyn Cheng and Daniel Sun. and we'll resume in 10 minutes. Thank you.